So we already know that linear algebra rules allow us to write a convenient way for writing systems of equations. So given this system over here, we can write it in what's called matrix form, where we have ax equals b, where A is composed of our equations, so equation 1, equation 2, and then each column corresponds to our unknowns. So here's our first unknown, here's our second unknown. Then our x vector is filled with our unknowns, so don't be confused between this x and this x. This x here is a vector of a bunch of letters. This x here is an unknown in my system of equations. And then B is filled with my constants from my right-hand side. Just some vocabulary. A non-homogeneous equation or non-homogeneous equation has non-zero values in our B vector. If there's only zeros in our B vector, it's called homogeneous or homogeneous. And we will see why this might matter in a couple weeks. So we can think about these systems in a couple different ways. So we can think about our systems of equations as lines, where each row or each equation corresponds to a given line. So if I look at this first line, it's going to be y equals x minus 2. Okay. It's going to look something like this. This second equation, it's going to be y equals 4 minus 2x. So it's going to look something like this. And this intersection point here is my solution. It tells me where my the solution is to both of those equations. So each row, all the way from A all the way to B, so 1, -1, 2, 2, 1, 4, that can correspond to a single line in my graph here. We can also think about them as vectors. So I can think about each column of A as its own vector, and then my B vector. So this first one is 1, 2, the second one is -1, -1, and then B is 2, 4. Whoops. So it's this one here. So it's not quite... Okay, yeah. Okay. So then my solution here would then be getting my vectors, scaling them up and along each line so that they match this endpoint. So we can see here my solution is going to be 2, 0. So same thing here. If I multiply this first vector here by 2, I end up at the tip here. This one needs to be multiplied by 0. It's not the best illustration. I will go over more illustration or another illustration in class. But we can think about it as lines. We can think about them as vectors, where each column corresponds to a vector, each row corresponds to a line. I can also rewrite this, and I can think about each equation as the dot product between the rows in A and the column in X. So if I rewrite that, it's going to be x minus y equals 2. It's my original equation. I took the dot product between this row and this column. Same thing for my second one. This row, this column. So 2x plus y equals 4. And so I can think about my equations as the dot product between my rows in A and my column X. I can also think about it as my columns being linear combinations, or my B being a linear combination of my columns of A. So I can rewrite it also as 1, 2. So this whole column multiplied by X plus this whole column, -1, 1, multiplied by Y equals my B vector. This here is a linear combination. It's a scalar times a vector plus a scalar times a vector to create another vector. In all of these situations, I'm solving for x and y. It doesn't matter what x and y are called. All I know is I need to figure out what x could equal, what y could equal in order to satisfy these equations.